Hi everyone and welcome back to my flight mechanics class. So today we're going to be covering the second building block leading to the equations of motion, and that would be the transformation matrices. So we're going to transform a vector from the inertial frame to the body frame and from the stability frame to the body frame as well. Now the question is, why do we need all of that? The EOMs are based on the sum of the forces, but how can you add vectors defined in different reference frames? The short answer is you can't. You can only compare apples to apples. If the EOMs are expressed in the body frame, then everything making up these equations needs to be expressed in the body frame as well, hence the transformations. Now the most complex transformation is going to be from the airframe or inertial frame to the body frame, reason being that it requires several consecutive rotations and several intermediate frames. If you want to transform a vector from the inertial frame to the body frame, you're going to need to rotate your inertial z-axis by an angle psi, the intermediate y-axis by an angle theta, and the second intermediate x-axis by an angle phi. Psi, theta, and phi are called the Arloy angles, and they basically describe the attitude in three-dimensional space of the aircraft with respect to the inertial frame. So psi is the yaw angle, theta is the pitch angle, and phi is the roll angle. These rotations will need to happen in that specific order because otherwise your intermediate frames are going to be different and the magnitude of the angles will be wrong. Finally, to transform a vector from the stability frame to the body frame, you'll have to rotate the stability y-axis by an angle alpha. So let's start with the first transformation, and that is going to be from the inertial frame to the body frame. So we're going to start with the airframe materialized by IE and JE, and we're going to rotate that by an angle psi or yaw angle to yield our first intermediate frame, and that is materialized by I prime and J prime. So we have a vector v expressed in the inertial frame and defined by its components xi, yi, and zi, and what we need to do is to project these components onto the new frame, that is both xi and yi onto I prime, and both yi and xi onto j prime. So the projection of xi onto I prime is going to be xi cosine of psi, and because the direction of that projection is in the same direction as the positive I prime axis, it is going to be a positive contribution. The projection of yi onto I prime is going to be yi sine of psi, and because the direction of that projection is also in the same direction as the positive I prime axis, it is going to be a positive contribution as well. Now the projection of yi onto j prime is going to be yi cosine of psi, and because the direction of that projection is in the same direction as positive j prime, it is going to be a positive contribution. Finally, the projection of xi onto j prime is going to be xi sine of psi, and because it is in the opposite direction of positive j prime, then it is going to be a negative contribution. Now, because we're rotating about the z-axis, z1 is actually equal to zi. So now we have enough to construct our first rotation matrix, and we can multiply it by our vector v expressed in the inertial frame, and that is materialized by xi, yi, and zi, and that will yield the new components of the same vector in the first intermediate frame, and that is x1, y1, and z1. On to the second rotation. So we're going to start with the first intermediate frame, and that is materialized by I prime and k prime, and we're going to rotate it by an angle theta or pitch angle to yield the second intermediate frame, and that is materialized by I double prime and k double prime. So what we need to do is to project both x1 and z1 onto I double prime, and both z1 and x1 onto k double prime. So the projection of x1 onto I double prime is going to be x1 cosine of theta, and it is going to be a positive contribution because the direction of the projection is in the same direction as the positive I double prime axis. Now the projection of z1 onto I double prime is going to be z1 sine of theta, but because the direction of that projection is in the opposite direction as the positive I double prime axis, it is going to be a negative contribution. The projection of z1 onto k double prime is going to be z1 cosine of theta, and because the direction of the projection is going to be in the same direction as positive k double prime, then it is going to be a positive contribution. And finally, the projection of x1 onto k double prime is going to be x1 sine of theta, and because the direction of the projection is going to be in the same direction as positive k double prime, it is going to be a positive contribution. And because we're rotating about the y-axis, y2 is going to be equal to y1. So now we have enough to construct our second rotation matrix, and we can multiply that by our vector components in the first intermediate frame, and that will yield the new components of the same vector, but this time in the second intermediate frame. And that is going to be x2, y2, and z2. On to the last rotation. So we're going to start with the second intermediate frame, and that is materialized by j double prime and k double prime, and that is going to be rotated by an angle phi or roll angle to yield the body axis system, and that is going to be materialized by j and k. So what we need to do is to project y2 onto j and z2 onto j as well, and then both z2 and y2 onto k. So we're rotating about the x-axis, so xb is actually equal to x2. Now the projection of y2 onto j is y2 cosine of phi, and the direction of that projection is in the same direction as positive j, so it is a positive contribution. The projection of z2 onto j is z2 sine of phi, and here again, the direction of that projection is in the same direction as positive j, so it is a positive contribution. The projection of z2 onto k is going to be z2 cosine of phi, and because the direction of the projection is here again in the same direction as positive k, it is going to be a positive contribution. Now finally, the projection of y2 onto k is going to be y2 sine of phi, and because the direction of the projection is opposite to positive k, it is going to be a negative contribution. So now we have enough to construct the last rotation matrix, and we can multiply it with the vector components in the second intermediate frame, and that is x2, y2, and z2, and that will yield the new components of the same vector, but this time in the body frame, and that is xb, yb, and zb. So now that we have all three rotation matrices, we can multiply all three of them by the vector that we wish to transform from the inertial frame to the body frame, and in this case it is going to be the weight vector. So it is going to yield this, and it is the same vector, but this time it is expressed in the body frame. The components are expressed in the body frame. So now onto the second transformation, and this time it is going to be from the stability frame to the body frame, and it is going to be a whole lot easier because we are only going to need one rotation. So we're going to start with the stability frame, and that is materialized by IS and KS, and we're going to rotate that by an angle alpha, or the angle of attack, to yield IB and KB, and that is going to be our body frame. So we start with a vector V expressed in the stability frame, and that is defined by its components XS, YS, and ZS, and what we essentially need to do is to project both XS and ZS onto IB, and both ZS and XS onto KB. So the projection of XS onto IB is going to be XS cosine of alpha, and because the direction of that projection is in the same direction as positive IB, it is going to be a positive contribution. The projection of ZS onto IB is going to be ZS sine of alpha. And because the direction of that projection is going to be opposite to positive IB, then it is going to be a negative contribution. We're rotating about the stability y-axis, so YB is actually equal to YS. That part doesn't change. The projection of ZS onto KB is going to be ZS cosine of alpha. And here again, the direction of that projection is going to be in the same direction as positive KB, so it is a positive contribution. And finally, the projection of XS onto KB is going to be XS sine of alpha, and because the direction of that projection is going to be in the same direction as positive KB, it is going to be a positive contribution. So now we have enough to construct a rotation matrix, and we can multiply it with our vector components in the stability frame to yield the new components of the same vector, but this time in the body frame, and that is going to be XB, YB, and ZB. So we can use that matrix to transform the aerodynamics forces vector from the stability frame to the body frame, and that is going to yield what you have at the bottom. So it is again the same vector, but it is going to be expressed this time in the body frame, and you can actually use that in your equations of motion. Alright, this is it for today. Thank you very much. See you next time.